In the previous video, we saw how we could solve this system using the method of substitution. In a nutshell, the method of substitution is as follows. You pick one equation, and then you write one of the variables in terms of the rest. And then in each of the remaining equations, whenever you see that variable, you replace it with the expression. And you'll get a system that has one fewer variable and one fewer equation. So you repeat the process until you get to a system that consists of only one equation or one variable. Now we're going to interpret the process as transformation to this system. So let me first label these equations 1, 2, and 3. And recall that we first wrote x1 in terms of x2 using the first equation. So x1 is equal to 1/2 x2. And then we replace x1 in equation 2 and equation 3 with 1/2 x2. And so we obtain this. Now let me rewrite this equation here. So I'm going to rewrite this as x1 minus 1/2 x2 equal to 0. And let me label these equations 4, 5, and 6. Now I can see from here that 4 is 1/2 times 1. This means that equation 4 is obtained from multiplying both sides of equation 1 by 1/2. And 5 is obtained from adding 1/2 times equation 1 to equation 2. So what this means is I take 1/2 the left hand side of 1 and add it to the left hand side of 2. And this is what we get on the left hand side. And 1/2 times the right hand side of 1 added to the right hand side of 2. And finally, we see the 6 is minus 3/2 times equation 1 plus equation 3. So again, what this means is you take the left hand side of equation 1, multiply that by minus 3/2 and add it to the left hand side of equation 3. And you do the same for the right hand side. Since the system consisting of the equations 4, 5, and 6 is derived from the system up here, every solution to the system up here will be a solution to the system down here. But the opposite is also true. If you take a solution to 4, 5, and 6, it will also be a solution to 1, 2, and 3. And that's because we can obtain equations 1, 2, and 3 from equations 4, 5, and 6. And it's not hard to see that to get from 4 to 1, you just multiply both sides of 4 by 2. And to get from 5 back to 2, you just subtract equation 4 from equation 5. And you can obtain equation 3 from equation 6 and 4 as well. So we haven't gained or lost any solutions by performing these operations. It turns out that the kinds of operations that appear here are actually sufficient to solve any system of linear equations. And let me write them down. So there are 3 operations. So the first one is multiply both sides of an equation by a non-zero constant. So that's the operation we use to obtain 4 from 1. And the second operation is add a constant multiple of an equation to another equation. And there's a third operation. It is not really necessary, but sometimes it's convenient to have this around, and it's to swap the positions of 2 equations. What this means is, for example, I can take the purple equation and place it as the second equation and the blue equation as the third equation. These operations actually have a special name, and they are called elementary row operations. And they're usually carried out on matrices. That's something that we'll look at in a later video. For now, let me use these operations to solve the following system. So in this system, Z and W are the variables, and the numbers are complex numbers. The first operation we're going to do is we multiply the first equation by minus I. And this is what we're going to get. Now I'm going to add minus 1 times equation 3 to equation 4. And this is what we get. And now if we look at equation 6, we know that W is minus 2 minus I divided by minus 1 minus 2I. And that's just 2 plus I divided by 1 minus 2I multiplied by 1 plus 2I divided by 1 plus 2I. So I'm multiplying both denominator and numerator by the complex conjugate of 1 minus 2I. And that will give me, so in the denominator I will get 5, and in the numerator I'll get 5i, and so w is equal to I. So now that we know w is equal to I, we can plug this into equation 5. So from equation 5, we know that z minus I times w is equal to 2, and that implies that z is equal to 1. So the solution is zw equal to 1i.